Okay, good afternoon to everybody. Welcome, thank you for being here for this ceremony of the Fondazione Sapienza Tomassoni Chisesi Prize for Physics. We need to run at the beginning, then we will have the seminar of the two winners of the prize. So even on behalf of the Tomassoni of the Fondazione Sapienza, I thank you for being here, and I give my the word to Professor Gaudio, the rettore of Sapienza.
Thank you very much. Good morning. Welcome everybody. It's a great pleasure and a great honor for me to be here, and on behalf of Sapienza University of Rome, my most cordial greetings on the occasion of this ceremony, in which the Fondazione Sapienza and Tomassoni Chisesi Prize will be awarded to recognize and encourage outstanding achievements in physics. It's a pleasure for me to welcome at Sapienza University of Rome Professor Philip Kim from Harvard University and Professor Scott Aaronson from University of Texas at Austin. Therefore, let me say just a few words to present you the University of Sapienza, that is a very old university. It was founded by the Pope, Bonifacius VIII, in 1303, and is one of the oldest universities in the world, and is one of the most important Italian and European institution, and also in university rankings. Today we are the largest university in Europe. We have more than 113,000 students, and we have more than 4,000 of professor researchers, and more than 8,000 of technical and administrative staff. So it's a so large university. It's quite difficult to manage it, but we try. So, and we have about 300 degree programs and 200 professional master courses. Sapienza is organized in 11 faculties, 60 departments, and many research centers that drive high levels of excellence in archaeology, physics, astrophysics, as well as humanities and cultural heritage, environmental studies, nanotechnologies, cellular and gene therapy, design, aerospace, and so on. We strongly believe in the internationalization of higher education, and we are deeply involved in the program of the so-called Bologna process to build up an European system of university and of exchange of researchers and professionals. So it's very important. I wish to thank Professor Antonello Folco-Biagini, that is the president of our foundation, Sapienza, and is very involved in organizing scientific and cultural events that are important for our colleagues, but moreover for our students. And I wish to give my best welcome to all young people here present to hear your presentation. So, Sapienza Foundation devotes all its resources to educational purposes, such as spreading knowledge, supporting and developing research in most important scientific fields, and today we'll award the Fondazione Sapienza Tomassoni Chisesi Physics Prize to Professor Philip Kim and Professor Scott Aaronson. Professor Kim is a world-leading scientist. His research area in experimental condensed matter physics, with an emphasis on physical properties and applications of nanoscale low-dimensional materials. The focus of Professor Kim's group research in the mesoscopic investigation of transport phenomena, particularly electrical, thermal, and the thermoelectrical properties of low-dimensional nanoscale materials. Instead, Professor Aaronson's research focuses on the capabilities and limits of quantum computers, and more generally on computational complexity and its relation to physics. His recent interests include how to demonstrate a quantum computing speed up with the technologies of the near future. In addition to research, he writes a widely read blog and has written about quantum computing for Scientific American, the New York Times, and other popular venues. I wish to thank, on behalf of Sapienza, of myself, Professor Philip Kim and Professor Scott Aaronson for being here at Sapienza University of Rome, giving the opportunity to our colleagues and to our students to listen to important lessons about stacking atomic layers and quantum computing. Thank you so much, everybody, and I'm sure this afternoon will be a very interesting occasion. Thank you so much, and good work.
Okay, I think we can start with the ceremony of the prize. So I will ask first Professor Kim.
Okay, now the prize is divided in two categories, one over 40 and the other below under 40. Now the winner in the first category is Professor Philip Kim of Harvard University, and the motivation is for his pioneering experiments on quantum transport in carbon nanotubes and graphene, which open new perspective in the study of physical properties of material at the nanoscale. Philip Kim is a world-leading scientist in research on nanoscale materials, two-dimensional singularities, van der Waals heterostructure, and low-dimensional architecture, and provided the groundbreaking observation of the quantum Hall effect in single graphene layer, contemporary to the result obtained by 2010 Nobel Prize winner Time and Nobel herself. Okay.
And now for the category under 40, Professor Scott Aaronson, University of Texas, Austin, USA. The motivation is for his strong contribution to define the fundamental limits of quantum computation with a number of pioneering works at the frontier of computational complexity and quantum mechanics. Ok. So, possiamo cominciare con i seminari? Sì. Possiamo cominciare i seminari, no? Ok. So I asked to Professor Kim to give the seminar. The title of the seminar is Sorry, I have here only the title in Italian. Costruzione di multistrati atomici alla ricerca di una nuova piattaforma di materiali per una nuova fisica. It's an Italian translation.
Yeah, okay. Thank you.
I want to thank the rector. He must leave very soon because he's going to go to Brussels. So thanks, rector, for being here.
All right. It is my great honor and pleasure to be here, and especially chosen to be the recipient of this very prestigious the prize. I like to thank the Tomassoni and the Chisesi family to create this prize to recognize the important work in the physics, as well as the committee to select me as one of this winners that added onto this long list of the very established the winners. I'm not sure whether I'm really entitled to get this prize, but anyway, it was a great honor, and then it was a great pleasure to be the members of this awardees. I want to actually discuss about some of this exciting development as a field, and including some of my contributions on the way, to show you that where we are in terms of the dealing with these materials and then understanding the physics behind of that. And that's a basic theme that I want to kind of present. And also, I was told that the audience of the talk probably is quite broad, so I will start with already a broad perspective, and maybe some of my colleagues that under this local expert may feel it's boring in the beginning part. Just please stay through toward the end. I will just try to also kind of cover some of this new development toward the end, right? Okay, so the title of the talk is about this stacking atomic layers, quest for the new materials in physics. And you will see that what I mean by the stacking atomic layers and what type of physics and beyond physics or the materials, right? Let me start with kind of some of the kind of general motivations, especially tied with some of the technologies, right? Probably in past 50 years or so, I think we've been observing that great breakthrough on the electrical engineerings and electronic devices, which will probably now tie down to some of the even more exciting development that you are going to hear from the next talk by Professor Aaronson about the quantum computing. But this development actually deeply tied with some of the material development. The modern days of the semiconductor chips, computer chips, if you just look at the inside, of course, it is rather complicated structures, and a lot of engineering is there. But in the nutshell, the core part of this modern electronics is based on the transistors, which is based on the semiconductors, right? So heart of this modern electronics is basically that core part, what you call this transistor, which is nothing but the electronic switches, right? Because we just kind of bring down this material in the so small scale, something like this tens of nanometer scale, that the transistor is actually shrink down quite a bit. This photographs I just downloaded from the internet is already pretty much outdated. It's only 10-year-old the microscope images, but now modern day of transistor is even 5 or 7 times smaller than what you just drawn here. It's like the 60 nanometers channel length. Now modern days actually commercially use the transistor inside my computer, your cell phone, is something like the 20 nanometers. It's much smaller than this length scale. But still, this length scale, tens of nanometer, is much longer than, much larger than atomic length scale. However, we are already getting really atomic length scale. In a sense, if you just look at what is the oxide thickness that control this the electrical path underneath, this getting down to the few atomic layers or few tens of atomic layers. About nanometer size of the oxide thickness is what is needed to control this transistor actions in this field effect transistor. So you already start to see that in the modern day of the electronics, engineers has been developed a way that we can control the materials down to a few atomic layers, and that becomes a really valid technical applications. In fact, over the time, the engineers, the material scientists, as well as some physicists, actually push down these techniques even further, and not only just making one layer, and the people actually have developed a way of the stacking materials called this the molecular beam epitaxy, which actually can create these atomic layers, many hundreds of the layers in extremely good control, right? So developed here is basically semiconductor heterostructures based on gallium arsenide, aluminum arsenide, or various different type of semiconductor heterostructures. People know how to stack these materials, many layers in very good different compositions, right? And they becomes quite kind of important in various technical applications. It turns out it is not only technical applications. Whenever you make this system such a precision with such a low dimensions, or that getting into this layered structures in confined few atomic layer, often the new physics actually start to arise. And we already seen many years ago, already 30 years ago, when people first tried to make this the very thin version of the transistor, different things happen. And this is photographs of the Klaus von Kliching, who is Nobel Prize winner of the 1985, should be changed it. But he did experiment in 1980 in the following experiments. What he did is just back then, the first set of this transistor, the silicon MOSFET is available. And MOSFET meaning that on the top of silicon, you just put down the thin gate oxide and gate electrode and applying the voltage. We know that simply it forms capacitors, which means that there is a sheet of the negatively charged carriers accumulated on the surface of silicon, right? And he tried to study that. What happened when you just put this system, or almost two-dimensional electron sheets, almost atomically confined, into the low temperature and high magnetic field, and just to study their dynamics. And of course, from elementary physics, we know that when you have the electrons or the charged particle start to move around inside the magnetic field, there is an effect called the Hall effect appears. In other words, there is a voltage start to develop orthogonal direction of the current flow, and that will just create this the Hall signal, which means that the signal across this current direction will increase as you increase the magnetic field. And the slope often tells you about how much carrier density you have in the system. So this is very useful things. But what he studied is basically what happened this Hall effect in extreme quantum condition, meaning that going to the low temperature and strong enough magnetic field. And to everybody's surprise back then, actually it was not just a simple Hall effect he saw, but it was actually a Hall effect with quantized steps that appears. And these steps that if you measure in terms of the resistance, it's nicely related with some of the integer number. In other words, first, second, third, and those kind of things is precisely quantized with certain the quantum numbers of the units of the quantum conductance. It's deeply related, in fact, to quantum mechanics. In fact, this is one of the first demonstrations that macroscopically you can detect something like quantum effect in simple your electronic devices. A little deeper studies soon reveals that this quantization of Hall resistance here is related with your wave functions of the electron. And particularly, as the complex number of the wave function, it has a phase. And the quantum number that is related with the step is nothing but how many times that this phase of the wave function is winding around under the quantizing under the strong magnetic field. In other words, this topological winding number of the wave function dictated the steps it has been observed into this system. Clearly demonstrate that it's not only technological evolutions that allows our transistors to make it small, but we start to kind of use that also study about interesting physics, especially interesting quantum physics in kind of interesting that extreme condition, right? So that has been kind of good example how that we can just kind of see that whenever we start to develop the new type of the material system, we start to understand some of the interesting physics that appears. Now, this is a good example that also when you just kind of reduce down the dimension into the lower than 3 dimension, something that we didn't experience at 3 dimension start kind of appears. Time flows, and many years after that also there has been the development of so-called nanotechnologies. And this is related with some of the even familiar materials. So when you reduce down the size, some of the interesting physics that appears that we didn't expect, right? And in some sense, this silicon MOSFET and looking at the quantum Hall effect is a good example, right? So you start with the known silicons, but simply you confine the electron into the very low dimension or surface of the silicon, you start to see that this clear quantum mechanical effect. One of these highlight of the nanophysics, I would say, is around 2004, where that groups in the Manchester's, Kostya Novoselov, Andrei Gaim, and found a way that you can extract a single layer of the graphene out of graphite and demonstrate that it can be a 2-dimensional materials, right? this discovery, that when I also worked on kind of similar times in this field, the material is rather surprising in a sense. Many people didn't believe that you can get this atomically thin materials rather easily. But the duo found a very easy way, so-called mechanical exfoliations using Scotch tape. The first demonstration is happened that you can actually extract a single layer of the graphene, and you can study those kind of material properties. So graphene, as a single atomic sheet of the graphite, is a rather unique system because it's rather simple. It's made only out of the carbon. They make this kind of simple chemical bonding called the sp2 bonding, where the 3 carbon atoms make the sigma bond, but the pi electrons remains that can be shared between them. So in a sense that due to this shared carbon electrons, that this graphene is rather good conductors. Right. It is a good conductor, but also you can see that electron is extremely confined in the atomic sheets. In some sense, this is the material, that thinnest material you can ever get in the universe, right? Because to get the material, you need atoms. Carbon is one of the smallest atom you can get, and this is known to be the only the chemical bond you can just realize as an isolated system, as a 2 dimensions, it can be stabilized. So I almost bet that this is probably thinnest materials we ever get, even in the future, right? In that regard, the electron that confined in system can be extremely the confined system in the 2D and almost behave like the 2-dimensional system, right? What is actually interesting and surprise is it's actually electronic band structures. In fact, although this material was extracted in 2004, people have been just speculating about the electronic property of this system ever since that people know how to compute the quantum mechanical band structures of the materials. In fact, it was Philip Wallace in 1947, almost more than this, now even almost 70 years ago, that using this block theorems, and he just compute this, what is the electronic band structure of the graphene look like. Of course, graphene was known as a basic units of the graphite, and that's the motivations that Wallace actually calculate what is the electronic band structure of the graphene. But discovery is rather startling because what you see here is basically a rather symmetric band on this type binding level. But what is important part is that the band structure is near this Fermi level, which is basically the middle point of this symmetric band. If you just zoom in that the band structures, turns out the dispersion relation, in other words, electron, the energy and momentum relation is rather linear. And the band has the spatial point where this top and bottom band meet each other, right? In terms of condensed matter physics language, you can say that this is a valence band and conduction band. This is the empty band and the field band. But as soon as you present this type of approximate band structures to anyone in the physicists start to notice that this is not only the electronic band structure graphene, but there's analogies you can immediately find. This is, you can see that the linear dispersion relation look like a particle that move at the speed of the light without mass. Often that if this is a fermion, like the spins exist, like the electron here, this is basically the band structures or the dispersion relation expected happens and when you have the Dirac like the particle, in other words, the fermions moves at the speed of the light, right? And that's precisely what type of the analogy actually works. It turns out this analogy is even deeper. If you just look at the Dirac equations, it's not only linear dispersion relation, the fermions of spin, in this particular case, should be the chiral. In other words, it should relate with the momentum directions of this particle. In other words, if you just momentum, if you have the moving particles in certain momentums, its spin is either aligned or anti-aligned, depends on whether this is particle whole, right? And that type of the analogy may also work in the graphene. It turns out it does. When we describe the electronic band structures of the graphene, turns out that we have to look at this, the detail of the so-called atomic basis. You can notice that if I just look at this hexagonal lattice structure of the graphene, you can categorize this carbon atom two different ones, depends on the chemical connections, chemical bonding directions, like I just painted out the red versus blue, and the red versus blue, they actually opposite chiralities. So although they are the same carbon atoms, their chemical bonding direction is different. So it's natural that when you just build up the wave functions, you have to build up the wave function is two different bases and form this block wave functions to build this the total wave function that describes electron in the graphene. What I'm trying to say here is it is very natural that when you just look at this graphene band structures due to this crystallographic symmetric, I need two bases that's sitting on the different type of the carbon atoms, right? So mathematical object that I need to describe this two componentness of the wave function is, of course, this spinner, which actually almost behaves like this spin half object in this case, right? So what you see here is even without even the real electron spin, when you just try to describe electronic band structure of the graphene, it's a very natural concept. I need to bring in this so-called spinner idea, that spinner as if the spin half particles comes in. And not surprisingly, when you just kind of connect all of these things, basically that your drag equation describe this the previous band I just showed you. This is not the real spin, but when you just take the spinner, or let me call the pseudo spin that describe wave function symmetry in this lattice, almost behave like this real spin Ross role in the drag equations. In other words, spinner, pseudo spin is chiralized, pseudo spin becomes polarized, depends on whether you are dealing with the electron versus hole in the band structures, or that one K pointer versus the other K point. Now that actually brings us very important ideas about the understanding or using this graphene for the real world. What I'm saying here is when you extract this graphene, that you will realize that the electron behave like as if this the particle that moves at the speed of the light without mass, but on the top of that this spinner that I just mentioned plays an important role to understand dynamics of the electron, right? Now, anyone learn about the quantum mechanics? The one thing that very peculiar things appears in quantum mechanics is in fact electron spin half object, something like this, right? Why it's peculiar is basically when you turn around the electron spins or with a spin 360 degree and comes back, something like that. I'm here, that I'm just spin myself around 360 degree, and you see that I didn't change it, right? However, if I just do that for the electron, it's not the case. Because the electron spins, when you turn around 360 degree, it doesn't come back its own, but it comes back with a sign difference. It's only that when you just turn electron twice, it becomes its itself. And that concept actually has been described in many different languages, but most general thing is basically so-called the Berry phase arguments, where that the quantum mechanics, the wave functions that describe spin half has a special properties that relate with this Berry phase, such that you just turn around twice the electrons, so that you have to come back its own. In other words, when you just turn around only 360 degree, there is always the phase of the pi appears due to this special Berry phase related with the spin half object, right? Now, I want to kind of show that indeed this is not only just our quantum mechanics textbook, but it actually appears in the lab, and you can detect that. How we can detect that? Well, if we just really believe that electron in graphene carries its pseudo spin with a spin half object, and that is polarized along the direction of the momentum, the claim is if you simply measure the quantum effect in graphene, then you should be able to measure it. How we can do that? So here is the real experimental data measured in my lab some time ago, right? I'm showing you the whole the effects as a function of magnetic field. I already briefly mentioned that in classical Hall effect, you expect this whole signal increases linearly, right? Now, in quantum Hall effect, where the material is a two-dimension, in other words, electron is confined to two-dimension and under the very strong magnetic field, low enough temperature, then Hall effect shows this plateau, right? So that's a Hall effect. However, this Hall effect I mentioned should be plateau like this 1, 2, 3, 4, because it's a related winding number. Now in quantum Hall effect, the graphene quantum Hall effect, indeed you get the Hall effect and plateaus, but But if you just look at this, how this integer increases, it's like the 2, you have to look at the denominator because it's a resistance, 2, 6, 10, 14, and those kind of sequences. Right? Okay, so this is integer sequences, but not clearly just a regular integer sequences. In fact, you can just look at the generalization of this, what this sequence look like. It turns out sequence goes like that 4 times of a half integer. Now it turns out this 4 is related with so-called the degeneracy in the band structures. There is a real spin degeneracy too, and there is that if you look at the cone, in fact the cone is not appearing as 1, but it appears as a pair. So again, those kind of what we call this the valley degeneracy 2 will give you the total degeneracy 4 there. So that I can explain that without too much of trouble. What is the interesting part is basically this is a half integer, right? To make this spatial sequence of 2, 6, 10, 14. Where this half integer comes from? In fact, this is a half integer precisely related with the body phase that related spin half. I told you that when just the spin is turning around 360 degrees, it doesn't come back its own. It come back with this phase difference, the sign difference in front of wave function pi, the -1, which will create in terms of phase is pi, right? And that's precisely that phase that only when you just turn around twice that you get this the 2 pi, which means 1 turn you get the pi. In terms of integer, that's basically you give the winding number shift about half integer, right? And that's basically the origin of the getting this special sequence in here. So what you see here is, again, another example. When you just reduce down the material thicknesses and getting to the extreme 2 dimensions, you get the interesting materials. But on the top of that, you start to see that some of the physics that we didn't see or we didn't expect actually appears. And that's kind of another good example that when you just kind of bring it down to the low dimensional system and study about the physics, often you bumped with some of the things that you have not realized in the lab scale. It turns out in past, say, 15 years or so, after that, the initial discovery of graphene, the field really exploded in the directions, right? Nature provides us not only the graphene as a materials that we get down to the 2-dimensional materials. Nature has given us many different types of materials that, in fact, just to do the very similar tricks and similar way that we can create the low-dimensional system. Graphene starting from the graphite. Right? And another way to say that is starting with the graphene, if you stack them together and give weak van der Waals interaction, you can turn into the graphite. Right? Nature actually provides us many similar layered materials that in principle, starting from this, the host materials that which actually stack them together already, nature given us, we can undo that stacking and create this atomic layer materials. It has been possible. For example, that boron nitride, which almost look like the graphite or graphene, except that 2 carbon atom unit cell is replaced by boron and nitrogen. You can stack these materials and can make this insulator. Another way is you just grow these boron nitride crystals, and then you can extract a single layer of the boron nitride, breaking these van der Waals interactions. It turns out you get the nice insulator. There are other type of materials. In fact, that's a start. There is a transition metal dichalcogenides, there is even the high temperature superconductor, some of these the organic materials, inorganic organic materials. In fact, it turns out that nature provides us millions of different types of the layered materials. In principle, you can just kind of using very similar technique to break this material down to monoatomic layer, and yet they are chemically stable, and create this 2-dimensional system, and you can study them. What is more exciting in some sense, is super exciting, is all these materials comes with a different flavor. Graphene, starting from the graphite, is a good conducting materials. It turns out this conical band structure make it is rather semi-metallic. In other words, it is metal, but it's not necessarily good metal. But turns out some of this material is semiconductor, either P-type or N-type. Some of these materials becomes metal, superconductors, strange metals such as developing charge density waves. Some of them becomes magnetic. So you can start to see that there are many different kind of materials actually do exist. It's not only stop there. We can actually imagine that starting from one materials, then we can just kind of bring the another material and just put them together and make these kind of structures that can build up This is basically idea of stacking up the materials, then which actually has been demonstrated in semiconductor MB system I just showed in the first few slides. But in principle, that starting from these things, you can just kind of do the very similar way to stack these materials. However, there's one big difference that what has been demonstrated in semiconductor heterostructure versus the possibility of using this to create some of this system. The difference here is basically between the layer there is no strong interactions together, and that's important because in semiconductor heterostructures grown by the MB, principle of the MB growth is related with epitaxy, which means that layer-layer interaction is important to just ensure that they grow as a layered system as well controlled. Another way to say that is that when I just have the one layer, there's only the finite choice that I can put in the second layer to make sure this, the vertical epitaxy actually worked it out. Unlike that, the MB type of the approaches, in principle, this Van der Waals system, because there's no or almost non-existence of the interactions between the layer, in principle, you can just kind of put them together with the various different type of the materials without considerations of the detail of the epitaxy. Indeed, that has been the case, right? Here's a good example. That we started with the graphene, but then we just put the boron nitride. We started with the boron nitride, put the graphene, and put the boron nitride. This can be done by just kind of techniques called what you call the Van der Waals stacking using these polymer layers. You break the crystals into the monolayer, and you pick them one by one, and create those kind of stacks of the atomic layer, right? If you just do it right, in careful manner in the lab, basically, you see that at the interface, there's no foreign atoms, and all these layers is basically kind of interfaced with extremely sharp interfaces, and I don't necessarily care about this chemical bonding between them. It's not only graphene and boron nitride. You can just do this in the many different materials. Here's the example, right? Here, the graphene is sitting on the molybdenum disulfides encapsulated in the boron nitride. Basically, we can create those kind of atomic scale heterostructures in rather easy way, I would say, starting from this breaking these materials, and we just kind of make them into these heterostructures, right? So idea is basically by just assembling this type of the atomic layer, can we make some of the functional structures, right? Like this, we started with the Lego blocks, and then each of the layer has a different functionality. In other words, different the electronic or magnetic thermal properties. Build them up together, stack them together. Can I just make the system that can be quite different from individual system? So that's interesting questions we can address in terms of engineering, right? Some sort of functionality sounds like the engineering. However, it is not only engineering questions, but important physics questions as well. Let me just kind of just challenge you with this the diagram. So in this diagram, I just kind of list the column and the row with some of the materials. Graphene, boron nitride, molybdenum disulfide is N-type semiconductor, tungsten diselenide is P-type. This is superconductor, this is charged dense wave, this is magnetic layers, is a topological insulator, right? I'm just repeating the same thing, right? And I ask the following things, right? We know that each of materials is what is electronic properties. How about the interfaces, right? Well, some of the interfaces is something that I know, like molybdenum disulfide with tungsten diselenide. Well, this is PN, so must be PN diode, right? Something like the PN junctions. Well, it's atomically thin, but nevertheless, it is physics is kind of rather easily figured out, probably, right? However, some of the interface is something challenging, and it's not clear that what is going to happen. For example, this is magnets, and this is superconductor. What is going to happen between magnets and superconducting interface? I mean, that they are competing each other for the ground states, right? Maybe there is a triplet superconductivity. There may be something, right? So what you see here is already some of the interface we just put them together becomes completely non-trivial. And on the top of that, it's not only just the different types of heterostructures. Even just the same material, say graphene to graphene, boron nitride. This homojunction, I expect, well, so this is the same material. So what do you expect if you just put them together? One important part is in the Van der Waals system, because there is no interaction, you don't have to put them together in the same direction of the lattice. In fact, it turns out you can just put them together with various different directions, so-called this twisting of the same lattice. Suddenly created same interface with the different functionalities, right? As you just kind of put them together, you start to create this even larger scale of this wavelengths of the modulation of the electron structures, what you call often the Moire length scale. And this will just kind of bring us rather different type of properties, potentially very exciting properties, right? Let me give you the one example quickly. Here that is a system that I just put the graphene on the top of the boron nitride. Boron nitride is an insulator. There must be nothing special things happen, except that graphene and boron nitride, their lattice matching is very close to each other. So if you just put the graphene on the top of boron nitride with a very small twisting angle between their lattice, you start to create this Moire that I mentioned, and this Moire length scale can be something like tens of nanometer. And this tens of nanometer length scale is important because when you apply the magnetic field, especially magnetic field is strong enough such that if the magnetic length or the flux quantum is related with the magnetic flux quantum is related with this unit cell length scale defined by the Moire, then quantum mechanically you expect something unusual things happen, because basically all the quantum mechanical properties, in a sense, there's tendency that try to repeat every time you plugged into the one flux quanta for the periodic unit cell. Indeed, when you measure quantum artifact in this kind of system, you immediately see that it's not just a regular quantum artifact we haven't seen. So rather some complicated things happens. So this is the density per unit cell, and this is magnetic field. This dark region is where you get the quantum artifact, and it cannot be explained simply just one numbers, that the winding number I just mentioned before. But turns out this can be only explained when you have the two quantum numbers. And where these two quantum numbers comes from. In fact, this problem was solved some time ago by Douglas Hofstadter's, claiming that this is a Hofstadter's butterfly, which actually related to a fractal energy spectrum that appeared when you have the two competing length scale, governed by, in this case, the spatial length scale that of the Moires, as well as the periodic structures coming from magnetic field that will just combine to describe this, the complicated patterns with beautifully only using two integer numbers. So you can view that this is more like the generalized the quantum artifact. It turns out this goes really even further. If you go to the extremely clean sample and the quantum conditions, those kind of the Hofstadter's butterfly features that I just mentioned becomes even more complicated and involved. Not only that, in extreme quantum condition, now you have this fractional quantum effect. This one of signatures, the strong electron correlation becomes important, appears, and they start kind of compete each other and creating so-called the fractional fractal quantum effect, right? So all of these things, kind of exciting new physics, also appears whenever you just start create this interfaces, kind of to creating this type of the system. So I promised that I'm going to stop at the kind of 35 minutes, and I have only 2 minutes remains. But I have so many slides that show this example, but I will stop in next 3 slides. Promise you, just kind of give you some more exciting example, right? So this is the device that concurrent device we are making in our lab. So there's 2 kind of devices, right? But now you can see that the sophistication we can just put up there, right? So I told you that we have the many stacks, we can stack them together. To make this device, this is only made of graphene and boron nitride, but not simply graphene and boron nitride. Graphene is here, boron nitride is tunneling layer, boron nitride is also dielectrics. Outside of that, we have the graphite gates. So altogether, this is about 7 layers that we put them together. And more important part is each of the layer has their own electrical contact. So it's not only just the 2 dimensions that stack them together, but I can address all of the layers together in that way, right? Next example here is why not just graphene and boron nitride? We can just do something else. I mentioned that tungsten diselenide, moly disulfide, and these are p-n type of semiconductor, except it's atomically thin. So we just put them together to make this thin, atomically thin, the p-n junctions. Put down this boron nitride and everything contacts, rather complicated devices, but in the end we can make this type of heterostructures where atomically thin all the atomic layers is contact. perhaps most heroic device is here, that this is probably 9 layers of this heterostacks. Now, this is a bipolar transistor made of P and P semiconductors, all of the layers in contact, top and bottom gates, and complicate things. But point here is we have now technology that creates such a complicated devices. Not only such a complicated devices, it turns out these devices start to show some of the interesting physics. The interesting physics that I want to kind of share is something like this. Let me show this slide and the final slide. Many physics phenomena that we've been working through is macroscopic quantum phenomena. One thing that I can tell you is superconductivity is one thing very exciting, because that's basically 2 fermions. You make the pair to make the Cooper pair to turn it to the boson, and let this boson condensate into Bose-Einstein condensations. But on the top of that, there are many other systems that one can create this compound, the bosonic system. For example, you can start with the 2 fermions, electron hole, and make them together and combine to make the excitons. And exciton as a composite fermion, a composite boson, also can condense it down. And in fact, in atomic physics, as well as strongly correlated physics, people start kind of look for the possibility to create this bosonic soup, that out of this combining the 2 fermions to create this macroscopic quantum states. It turns out those kind of heterostructures I mentioned, right? For example, the atomic p-n junctions, we can create the excitons which can long live, and they can, in principle, can condensate into Bose-Einstein condensations. The other system that I want to kind of show you, end with my talk, is probably this system. Let's see. This is a system, 2 graphene layer under the magnetic field, right? And then you can create the Landau levels and top and bottoms of this the graphene layer. And then if Landau level is partially filled, you can create this electron like the Landau level, hole like the Landau level, right? And if those 2 layers are getting very close on the strong magnetic field, the electron and hole can couple to form the magnetoexcitons. Once you just kind of applied enough strong magnetic field, and they can condense into the Bose-Einstein condensations or magneto-Bose-Einstein condensations, and then something unusual things happen. Unusual thing in a sense that when you send the current in one direction and current in opposite direction, this is what we call this counterflow geometry, then you can start to make the exciton start kind of moves in only one directions. And since this exciton as a composite boson is condensated, when these things happen, there is no resistance then to the exciton motion, like the superfluid, right? Which means it's an interesting case. Each of the Landau level is half here, so it is compressible, it is resistive. But when you couple these 2 Landau level and send the current in opposite direction, suddenly you have dissipationless currents, like the superconductors. And that's precisely what is happening in this phase diagram. I'm measuring so-called this counterflow resistance as a function of magnetic field and the temperature. And this blue part is where you don't get any of the resistance, like the superconductor, right? And then, of course, as you go to the higher temperature, then you get the finite resistance. So we see that this transition is happening. But this transition regime is not straight, but it has some interesting shape. It's like the dome, like the shape. Anyone work on to the high temperature superconductor soon realize this is very close to what you are seeing, the high temperature superconductor. And some of the suspect or some of the theory there is maybe in high TC, where you have a conventional superconductor versus non-conventional, it may actually go through the BC and BCS type of the crossover, which actually shows very similar physics that we are seeing in this kind of graphene system that are mapping out this type of condensation and non-condensation states. So that's another good example that when you just create this rather complicated system, suddenly you start to get this kind of physics that you have not explored before. So I think that's kind of what I want kind of deliver the message. So going back to the diagram or the table, I just kind of only give you a few spots on this table as a potential interesting physics that appears, right? But you quickly see that many of these things that we just studied is not only the physics, maybe eventually the related with some of the applications. some of the robust quantum mechanical behavior we can realize this interface, maybe can be quite useful for the realizing interesting the devices based on the quantum mechanics. All right, so with that, I want to kind of thank my groups that make this the presentation is possible, and also I also take that this recognitions that I'm getting today is not because of my efforts, but actually my group efforts that kind of these talented young people. Thank you very much.
We have time for questions.
Thank you for a nice talk, very interesting. I have a question regarding the last part about the fake superconductor, if you want. As you know, in the superconductor, you don't just have zero resistance, but you have the diamagnetic response, which is the signature that something is condensing, which is the phase of the electrons. What would be the analogous here in this case?
All right, so in a sense, this one is, okay, very good question. So in the superconductors, basically we're under the magnetic field, you have the Meissner effects, and then eventually HEC2 will break these things. Now, in that regard, it's not kind of completely analogous to the superconductor in a sense. It is more like the analogous to the condensation of so just the real excitons. If you have the real excitons and then make the condensations, and then that's more analogous to this magnetic excitons case. However, that shares with some of this the similarity with the superconductivity in the following way, right? So this transition, especially in this is what we call the BC-like and BCS-like the transitions, and here the transition is happening through the creating this the vortex and anti-vortex pairs and unbinding event. Basically, it's the BKT transition is basically the transition mechanisms there. So if you just look at there, if you look at this transition very carefully, that on this high magnetic field, the counterflow resistance actually drops extremely sharp, as if that is look like the really superconducting transitions, right? But I would say this is still analogies rather than really direct connection with the 2D superconductivity, because it's not the Cooper pair, but it is electron hole form the excitons, and this excitons start to interact to make this the condensation. So it's not the Cooper pair condensation, but this exciton condensation. In that regard, I don't have London equations that give you the Meissner effect type of the effects here. In fact, the magnetic field is one of the necessary ingredients to form this exciton itself, right?
Any more questions? Okay, if not, we thank again.
Thank you very much. Yeah, thank you.
So now we have the talk of Professor Scott Aaronson. The title is 3 Questions About Quantum Computing.
Okay.
Hello.
I need the clicker. Okay. Oh, this. Okay. Okay, thank you so much for this amazing honor. So when I did a Google image search for quantum computer, this was one of the first things that came up. Now, I don't think that that's what they look like, but I should warn you, unlike Professor Kim, whose beautiful talk that we just heard, I am not a physicist or an engineer. I'm a theoretical computer scientist. And in fact, I've been praying that the committee will not choose to revoke my prize once they hear this talk and see, the enormity of the gaps in my knowledge of physics. For me, I know quantum mechanics pretty well, but only after you've sort of taken most of the physics out of it. And you view it as a sort of a generalization of the rules of probability themselves, from non-negative real numbers to complex numbers, which then changes the possibilities for information processing. So that especially, the honor of getting this physics prize while not being a physicist really leads me to say thank you to the Tomassoni and Chisesi families, of course, also to the committee, to my advisor, to my other teachers, my students and postdocs, my colleagues at UT and around the world, and the quantum information and theoretical computer science research communities, and my wife and my 2 children and my parents. I was actually just talking to my mom last night about my grandfather, who was here in Rome 73 years ago. He was a mine clearing engineer with the U.S. Army, which ironically, if you were a Jew in Europe at that time, was one of the safer situations to be in. If he'd known that his grandson all these years later would be back in Rome to accept an award for research in quantum computational complexity theory, well, I'm sure he'd have a number of questions about that. But one thing that I remember clearly was that he was always full of effusive praise for the warmth of all the people who he met in Italy, and that they shared food with soldiers who didn't have enough rations, even who were technically on the opposing side, and so that warmth is something that I get to experience every time I'm here, and certainly the food part. Okay, so let me move on to my first question that I promised to talk about, which is how could we demonstrate a speed up, ideally maybe even a useful speed up with a quantum computer in the near future. I mean, quantum computing is something that you've probably heard about in the popular press. It's there have been sort of breathless articles about it for 25 years now, and you may wonder, well, then where is it? Where are these amazing speed ups that we've been promised, right? The idea sounds great, that you will build computers that will be based on be able to take advantage of superposition. And a computer with only n bits would be able to have a superposition of 2 to the n power different states, and you could then exploit interference among 2 to the n different amplitudes, potentially in a way that would take a classical computer, an exponential and n number of steps to simulate, and yet you could do that using only, say, n steps or n squared or whatever. For me personally, I have to say, the number one application of quantum computing, more than simulating quantum physics and chemistry, more than breaking public key cryptography, more than optimization, anything else, is just disproving these people who come to my blog and say that quantum computing is impossible. I would like them to have to come face to face with the full reality of quantum mechanics. I know that there are other applications too. For me, those are the icing on the cake. So this goal of just demonstrating that a quantum computer can do something anything much faster than a classical computer, I mean not just in theory but in practice, has recently acquired this rather unfortunate name of quantum supremacy. This was coined by the physicist John Preskill in 2012. This was before, unfortunately, in the US we had reason to get reacquainted with this word supremacy. But people have wanted to rename it to quantum inimitability, but that's too hard to pronounce. Quantum ascendancy, but that just sounds like we're some cult. So we're sort of stuck with this. So how could we achieve this quantum supremacy? Okay, well, maybe the most famous example of an exponential speed up that you can get via a quantum algorithm was the famous discovery of Peter Shor from a quarter century ago. And Shor demonstrated that a quantum computer, if you could really build a scalable one with as many qubits as you wanted, and if you could if it had no noise, or if at any rate you could make the noise arbitrarily small using error correction, then you could use it to factor integers. So factor, let's say, an n-digit integer using a number of steps that scales only like n squared. Whereas the best known classical factoring algorithm uses a number of steps that grows exponentially, actually with the cube root of n. Okay, so this got a lot of people interested in quantum computing who hadn't been interested before. This has the implication, beyond number theory that once you have a quantum computer, you can break essentially all of the public key cryptography that's currently used to secure the internet. Okay, lest anyone get too worried, I hasten to add there are what we think are quantum-resistant crypto systems currently under development that we could migrate to, and some people are advocating that we start migrating to those systems now, even if quantum computers, of this scale might only become a reality decades in the future. But are those who's to say that those other systems are truly secure against quantum computers? So, well, that's a question that we'll come back to. Okay, but at any rate, maybe the interest of all the intelligence people in quantum computing maybe cooled a little bit when they realized just how hard it is to actually build these things. So I like to say, as far as I can see, it is ultimately possible to build a quantum computer, or if not, then that is much more exciting than if it is possible, right? If there's a deep reason why it can't be built, then that would be a revolution in physics. Okay, so believing it can be built is just a more conservative possibility. Okay, but that is not to say that we know how to build a truly scalable one anytime soon. And the problem is that if you really need to do error correction to get the accuracy, get the quality of your qubits to be close to perfect, then as far as we know today, that may require thousands of physical qubits for every logical qubit. So then if you're talking a few thousand logical qubits to break cryptography, you'd be talking millions of physical qubits. Okay, maybe that is possible, but it's not going to happen next year. Okay, so in the meantime, the question has arisen, isn't there some more immediate way to demonstrate the reality of a huge speed up with quantum computers that we could build over the much nearer term, like for example with 50 or 60 or 70 qubits. Okay, and what many of us realized starting a decade ago is that if that's the question you care about, then there are a lot of advantages to switching attention from problems with a single right answer to what we call sampling problems, where the goal is to output a sample exactly or approximately from some probability distribution over n-bit strings. Okay, just imagine just letting your quantum system just do what comes naturally to it, which is exhibit some probabilistic behavior, and we will then, as computer scientists, we will then take upon ourselves the challenge of arguing that a classical computer would need an exponential amount of time to output samples from that same distribution. Okay, so can we actually do that? You know, how would we know? As in both, how would we know that we actually were sampling from this distribution? And also, how would we know that it really was hard to sample with a classical computer? Okay, so those are the questions that some of us started thinking about a decade ago. And so my student Alex Arkhipov and I in 2011 sort of laid some of the theoretical foundations for this subject with a proposal that we called boson sampling. So this was a very, very rudimentary type of quantum computer. So it is not almost certainly not universal for quantum computation. Can't do, you know, arbitrary quantum computations. In fact, not even universal for classical computation. Okay, all it is you generate a bunch of identical single photons. You then send the photons through a network of beam splitters and phase shifters, so linear optical elements, and you then measure the photons to see, you know, how many photons have landed in each output port. Okay, and you know, the result will be probabilistic. It might be different each time you run the experiment, but you're interested in getting samples from the distributions over possible photon numbers, and that's it. Okay, that's the whole computer. But now. What got us interested was you know, a beautiful observation that was made in the 1950s that the amplitude, you know, if I have n identical photons and I want to know the amplitude for them to get from a given input state to a given output state, well then I have to sum over all n factorial possible ways of permuting those photons, and because they're bosons, you know, I just take a sum over each possibility, and this leads to a famous function of an n by n matrix, which is called the permanent. Okay, if you've seen the determinant, well, it's the same thing, but without the minus signs. Okay, and the permanent is a famous hard function in computer science. It is known to be very, very high up in the sort of hierarchy of computational problems. Okay, now, crucially, you know, we are not saying here that this boson sampling computer lets you actually calculate the permanent of a matrix of your choice. Okay, the problem is that the permanents only show up as amplitudes, which means that what the experiment really does is it just samples a random matrix, but in such a way that matrices with large permanents are more likely to be sampled than matrices with small permanents. Now, what is that good for? Well, I don't know. Okay, but what we did is we said, let's just take seriously what this system does. See, would it be hard for a classical computer to do the same thing? And so our main theorems that we proved were that, first of all, this simple optical setup could sample probability distributions that cannot be sampled by any polynomial time classical algorithm, polynomial time being our sort of rough criterion for efficient in computer science, like, you know, the number of, using a number of steps that's like n, the number of photons raised to a fixed power, unless something believed to be very, very unlikely happens. The polynomial hierarchy collapses. If you don't know what that means, you could take my word for it that it's bad. Okay, but if you've heard of P, you know, the P versus NP question, it would be almost as bad as P equals NP, or, you know, I guess that maybe to some people that's good, okay, but almost as incredible as that, but maybe just sort of at a higher level up. So it's, you know, in the present state of knowledge of computer science, that's about the strongest evidence that you can get that a problem like this is hard. Okay, but then, you know, the more physically relevant question was, well, what about a classical algorithm that just approximately sampled from the distribution, right? Because, you know, no experiment is going to be perfect. So we spent a lot of time studying that as well, and we could not get a result that was quite as clean as for the exact case. In fact, that remains maybe the central open problem in this subject. Okay, but we could show that even an approximate classical algorithm would have unlikely complexity consequences as well. Okay, so you know, we were just interested for mathematical reasons, but once we published this, a bunch of, you know, quantum optics experimenters got all excited, and they said, hey, you're talking about bosons. We have bosons in our labs, and we can try this out. And so then they started doing experimental demonstrations of boson sampling, initially with 3 photons, most recently with up to 6 photons. Now, if you really want to exceed the capacities of a classical computer, you'll probably need to scale up to about 50 photons. Okay, and scaling it up turns out to be really hard, mostly just because of the unreliability of the single photon sources that exist today. They don't spit out a photon exactly when you want them to. Okay, but if we get better single photon sources, this could be one route to achieving quantum supremacy. Okay, but it no longer looks like the one that is most likely to get there first. So there's been a huge amount of excitement in quantum computing in the last few years. Right, this is maybe the most exciting time for the field since some of the basic concepts were first discovered in the mid-90s. And the reason for that is that a bunch of the experimental groups, for example, at Google, at Microsoft, at IBM, are actually building systems now at Maryland that might be able to get into the regime of quantum supremacy of 50 or 60 qubits. By the way, I forgot to mention, I should have, but some of my favorite boson sampling experiments have been done right here in Rome. And actually, I'll be visiting tomorrow the group of Fabio Schiarino and to talk about what we can do and what we can demonstrate. Okay, but in the meantime, so there's a lot of excitement about superconducting qubits. So Google has announced plans to build a chip with about 72 pretty high quality superconducting qubits with controllable couplings. They said that it will be ready in a year. On the other hand, they said that more than a year ago. When I talk to experimentalists, I've learned to multiply whatever time frame they give by some factor. So let's just say within 1 years, a constant number of years, Google is planning to have a programmable 72 qubit quantum computer. Okay, and the funny thing that's been happening is that they and the others like IBM and the various startup companies, have been coming to the quantum computing theory community and saying, look, once we have these devices, what do we do with them? The first thing I think that it makes sense to do is just prove that the device does anything faster than a classical computer. After that, you can worry about doing something useful, right? There's a very simple proposal that some of us developed for what to do, which is sort of inspired by boson sampling, but which is more adapted to superconducting architectures, which is basically that you just put a random quantum circuit on your qubits, so like a random sequence of 1 and 2 qubit unitary transformations. You then apply that sequence, of unitaries over and over. Each time you apply it, you get a sample from some probability distribution over, let's say, 72-bit strings. Okay, so you find a bunch of these samples, and then you challenge skeptics. Well, if you don't think we're getting a speed up, well, then you sample from this distribution quickly. Okay, so so basically, you're sampling from a distribution that has an enormous amount of randomness, but it's not uniformly random, right? Some outputs are a little bit likelier than others because some outputs enjoy constructive interference while the others suffer destructive interference. So what you see is a speckle pattern like this. The same sort of thing you would see if I took a laser pointer like this one and I sent the laser through a bunch of ground glass, right? You would see some, sort of bright points and other dark points. And, and so we're interested in, looking at a collection of samples you get out and then testing, are they consistent with this specific speckle pattern? And moreover, is finding samples that are consistent with the specific speckle pattern that corresponds to a given circuit, is that a hard task for a classical computer to do? So in work with an undergraduate at the time, Li Ji Chen, a year ago, we proposed a concrete test for experimenters to apply to the outputs of a random quantum circuit. We called it heavy output generation, or HOG. You basically just calculate the ideal probabilities for your outputs with your classical computer, investing 2 to the n time to do so, and you see whether they exceed some threshold. Okay, now you may say, well, if I need exponential time with my classical computer, doesn't that defeat the purpose? Well, with 70 qubits, you can, if you're Google or IBM, you can do 2 to the 70 with enough effort. You can't do 2 to the 1,000. Okay, so it exceeds a Google, you could say. Okay, so this is very much an application, an experiment designed for near-term quantum computers, where the classical computer could simulate it, but it would take it a much greater amount of time. And then what we did is we gave a plausible-looking complexity assumption, which is just about a decision problem with a yes or no answer. And we showed that if you believe in the hardness of our decision problem, then actually it is indeed exponentially hard for a classical computer to do anything that would pass this HOG test, whether or not it is sampling from the right distribution. Okay, and so what Google is actually planning to do over the next couple of years, once their device is ready, is actually very closely related to this. So we've been trying to provide some theoretical foundation for it. Okay, now, my line until very recently, until just this year, was that obviously these sorts of experiments have no application in themselves to anything, right? Their only purpose is to prove that quantum computing works and disprove the people who say it can't work. Okay, over the last year, that has changed. And some of us have realized that, that actually as soon as you achieve quantum supremacy, even with just a 70 qubit device, there is already at least one useful application that you can get from that. And that application is to generate cryptographically certified public random bits. Okay, so it's very easy to generate random bits by quantum mechanical means. That's sort of baked into the theory. Okay, but if you were publishing those random bits over the internet, how could you prove to a skeptic that they really were generated randomly? Okay, well, quantum supremacy experiments provide a possible path to doing that. What you could do is you could have a classical client sort of repeatedly generate challenges, for example, pseudo-randomly, send them to a quantum computer, where each challenge, think of it as a quantum circuit for which the quantum computer is supposed to solve this HOG problem. Okay, and so then the quantum computer, is demanded to send back a response within a very short time, like let's say half a second, okay, and then the classical client sends the next challenge, and so forth. And then the classical client can pick a small number of these challenges, check whether they indeed solved the HOG problem, and then if they did, then what we show is that if you believe a plausible computational hardness assumption, and if the server is merely a quantum computer and not some science fiction thing that's beyond that, then it could only have passed your HOG tests by actually generating the samples randomly. Okay, there was no deterministic way, even for a quantum computer, to pass the test efficiently. Okay, so in this way, you could get sort of provably random bits, which you could then use for cryptocurrencies and various other applications. So this is not, maybe it's not the most important application in the world, but this might actually be the first application of quantum computing that will become feasible. That actually depends on the quantum computer doing something faster. Okay, so let me move on to question 2. So, I mean, it sounds like, when you read popular articles, sounds like, they often present a quantum computer as being able to do pretty much anything whatsoever, right? Or at least, any search problem at all. They could just try every possible answer in parallel, or maybe in a different parallel universe and just pick the best one, and that sounds amazing, but it also sounds like if it's that simple, why did you need all these people to, like Peter Shor, to think so hard about inventing quantum algorithms? Okay, well, it's not that simple, and one of the main things that we've known since the 1990s, but that has been very hard to sort of get out into the popular discussion of quantum computing, is that even quantum computers would face significant limits, and that there are important problems that seem to be intractable even for a quantum computer. Okay, so we have this hierarchy of complexity classes in computer science, P and NP. The holy grail is these so-called NP-complete problems. And then BQP stands for bounded error quantum polynomial time. It's like the quantum generalization of classical polynomial time. I drew it with this wavy boundary because everything quantum is spooky and weird. We're still trying to figure out exactly where it fits. It contains some problems like factoring that are not known or believed to be in P, but crucially, factoring is not thought to be an NP-complete problem. And Shor was only able to develop his fast quantum algorithm for factoring by choreograph the interference pattern that revealed the answer by exploiting very, very special regularities in the factoring problem. And they don't seem to extend to any known NP-complete problem, okay? So that has seemed to remain out of reach, even for a quantum computer, okay? And we get more insight into it by looking at maybe, the second most famous quantum algorithm after Shor's, which is called Grover's search algorithm, okay? So what Lav Grover discovered was that a quantum computer can search a list of n elements, should be little n, for a single marked element using only about square root of n steps. Okay, classically, of course, you'd need about n steps if you don't know anything more than just picking list elements one at a time and seeing whether they're the one that you want. Okay, which is sort of an abstract model for these super hard search problems like NP-complete problems. Okay, but now we also know a very, very important theorem due to Bennett, Bernstein, Broussard, and Vazirani. And they showed that if your list can only be accessed as a black box, and you sort of don't know anything more about the structure of your search problem, then Grover's algorithm is the best that even a quantum computer can do. Okay, they actually proved that before Grover's algorithm was discovered to exist. Okay, but even a quantum computer needs like square root of n steps for searching. The way that they prove that is, by sort of noticing that if you just move the marked element around, on average, only about 1 over square root of n amplitude in your quantum superposition is going to notice that, and it's not going to like chaotically blow up because quantum mechanics is a norm-preserving and linear theory. Okay, so you can just add 1 over square root of n amplitude onto your marked item at each time step, and then you need square root of n steps to get a large amount of amplitude there. What's the popular view of a quantum computer? That it just tries every possible answer in parallel. Okay, well, in some sense, that's true. Right? You create a superposition over all the possible answers. The problem is that if you want your computer to be useful, well, at some point you've got to measure it. And if you just measured an equal superposition, not having done anything else, then quantum mechanics says that all you're going to see will be a random answer. If you just wanted a random answer, you could have picked one yourself with a lot less trouble. Okay? So, you actually have to do something to concentrate more amplitude on the solution that you want. And this BBBV theorem is bounding the rate at which that can happen, at least for black box search. Okay, and this has all sorts of important applications. In my protocol for getting certified random bits from a quantum supremacy experiment, I'm actually appealing to this BBBV theorem to argue for why it's secure. Right? So I'm not only using the capabilities of quantum computers in that protocol, I'm also using their limitations. Okay, but now a lot of the work that I did in grad school when I first got into this field was aimed at understanding the limitations of quantum computers, or as I like to put it, the study of what we can't do with computers that we don't have. Okay, and so, you know, and it turns out that you know, there's more, you can say, than just the optimality of Grover's algorithm. So consider the so-called collision problem. Okay, where here I have a 2-to-1 function. So I have a list of numbers where every number occurs exactly twice, let's say. And my goal is just to find any collision pair, any pair that collides, like those two, for example. Okay, so you know, this models the breaking of one of the basic building blocks of modern cryptography called collision-resistant hash functions, and has many other applications. Even with a classical computer, this problem can be solved in about square root of n steps if your numbers are from 1 to n, because of the famous birthday paradox that says, you know, if there's about 30 people in a room, there's already a very good chance that 2 of them share a birthday, because what matters is the number of pairs, right? So, okay, now Broussard, Hoyer, and Tapp in '97 noticed that you can somehow combine the square root speed up that comes with Grover's algorithm with the completely different square root speed up that comes from the birthday paradox, and you end up with a quantum algorithm for this collision problem that takes cube root of n time. I'm not making that up. Okay, but then the question arose, well, why couldn't there be an even much better quantum algorithm, right? Maybe even one that just makes only 1 or 2 queries, independent of n. Okay, if you think about it, there almost is such an algorithm, right? Like I could just create a superposition like that, you know, compute my function f on a superposition of all n inputs, and then measure f of x, and what I'll be left with in the first register is an equal superposition over some collision pair, some x and y, such that f of x equals f of y. Now, all I would have to do is measure that state twice, and I would be done. Okay, if I could just measure that thing twice. You know, but, well, darn, quantum mechanics doesn't let me do that. Okay, and that's the whole problem. But, you know, we're not looking for a needle in a haystack, just for 2 identical pieces of hay. You know, and, you know, in fact, every 1-to-1 function differs from every 2-to-1 function on, you know, a huge number of places. So we can't make any argument that just based on the difficulty of noticing a local change, the way that BBBV did. Okay, so what I showed was that any quantum algorithm to solve this collision problem needs to make at least n to the 1/5 queries to f. Yao and Shi shortly afterward improved that to get the optimal result of n to the 1/3. The proof used what's called the polynomial method, an inequality due to A.A. Markov from the 1880s. That basically you say, suppose we had a super fast quantum algorithm to find collisions, well then surely it could also distinguish a 1-to-1 function from a 2-to-1 function. Because, you know, a 2-to-1 function has the collisions to be found. A 1-to-1 function does not. We could then take that algorithm and try running it on 3-to-1 and 4-to-1 functions and so forth, even though those occur nowhere in the problem statement. Okay, but then, you know, if we look at the probability of the algorithm saying yes as a function of k on a random k-to-1 function, we find that that leads to a low-degree polynomial of a type that one can then show cannot exist. Okay, so just, you know, I think I'm not going to get to my third question, okay, but let me just finish question number 2. You know, so this collision lower bound, right, you know, I was doing it for sort of internal reasons in quantum computing. What I did not expect was that it was going to have anything to do with black holes, okay, but then in 2012, the quantum gravity community was rocked, or, you know, set ablaze by something called the firewall paradox of Amhiri et al. Now, this was a thought experiment. It was sort of like a modern refinement of Hawking's black hole information loss paradox. And it was a certain thought experiment that involved an observer, Alice, waiting outside of a black hole for the black hole to mostly but not completely evaporate into Hawking radiation, which might take, for a black hole the mass of our sun, might take about 10 to the 67 years. We assume she has a really long grant. Okay? She then routes all those photons into her quantum computer, processes them in a certain way. She observes a certain structure of entanglement. She then jumps into the black hole, and all the accepted principles seem to predict that she would then observe a breakdown of space-time already at the event horizon. So she would never even get anywhere near the singularity, okay? And this conflicted with our understanding of, general relativity and quantum field theory. So people were very confused for a while. But then Daniel Harlow and Patrick Hayden wrote a remarkable paper in 2013 where they argued that to actually do this experiment that would create the firewall at the event horizon, Alice would need to do a quantum computation that would take exponential time, exponential in the number of Hawking photons. Okay, so we're talking now 2 to the 10 to the 67 years. So she could barely even make a dent on the problem before the black hole had already evaporated anyway, right? Which was sort of an amazing, to me, way of analyzing the problem. But when it came to the crucial point, well, why is the problem so hard for Alice? How do we know that it's hard? Even if she has a quantum computer, they appealed to the collision lower bound. So then, I was forced to learn something about black holes, and I actually improved their argument where it no longer needs my result anymore. But that's how it goes. Okay, so I did many other things about limitations of quantum computers. One of them was what's called the direct product theorem for quantum search. It says if a quantum computer is looking for many marked items in a list, but it doesn't even have enough time to find one of them, then the probability that it's going to find all k of them decreases exponentially as a function of k. Okay, that seems intuitively reasonable, but proving it required bringing in some new techniques. Well, I used the polynomial method, but in this case, I needed an inequality from the 1890s due to A.A. Markov's younger brother, V.A. Markov. And an implication was that of this direct product theorem was that in the black box setting, there cannot even exist a magical quantum advice state, left over from the Big Bang or whatever, such that if we had it, then it would make NP-complete problems easy to solve with a quantum computer. Okay, so without exploiting the structure of an NP-complete problem, they won't be easy for quantum computers, even in the presence of some magical quantum advice state. Intuitively, because you've got to measure the state at some point, and then you only get out a very limited amount of information. One can, the connection is that if this advice state were possible, then one can just guess the advice, fill in some random garbage in place of the advice, and then one could just run the algorithm over and over, and one would get a contradiction with this direct product theorem. Okay, so my question 3 was, is there anything beyond quantum computing? I'm probably going to have to skip that unless anyone wants to ask me about it in the question period. But I can sort of whet your appetite with these beautifully rendered slides. The quantum version of the extended church touring thesis, the relativity computer, the Zeno's computer that does infinitely many computations in only 2 steps, the time travel computer, which I actually have a paper about with John Watrous, not the one that I based my tenure case on, the stochastic hidden variable theories that extend quantum mechanics by postulating a hidden variable, and one can then ask, if you could see the entire history of the hidden variable, what could you then efficiently compute? And that turns out to lead to a model of computation that is more powerful than quantum computation, but only a little bit more powerful. And it's almost the only example that we have of such a model. Okay, it lets you solve the Grover search problem in cube root of n time, for example, instead of square root of n, but probably not faster than that. Okay, and it lets you solve certain problems like graph isomorphism that we don't know how to solve even using a quantum computer. Okay. So let me just summarize. We may soon have 50 to 70 qubit quantum computers that do something that we're pretty confident is faster than a classical computer. Now, conceivably, even something useful, like certified random bits, although threatening public key cryptography and applications like that will probably take a lot longer. Contrary to a widespread misconception, quantum computers will not just magically speed up everything. We still have to think about it. Okay, they will often get Grover-type speed-ups, like square root type of speed-ups, for a very wide range of problems, including optimization, machine learning, and all sorts of applied problem domains. But if you want exponential speed-ups, the complete game changers, those seem to depend on finding problems with a much, much more special structure for which you can choreograph this interference pattern. So few problems from number theory and group theory, like factoring and discrete logarithms, seems to have that structure. Simulating quantum mechanics itself certainly has that structure. But contrived problems like boson sampling have that structure. Okay, but we're still looking for more examples. And then if you wanted to go even beyond quantum computers, well, that seems like it would probably require some new physics beyond quantum mechanics, which who knows if that exists. And I think we should be skeptical of any computational model that would just make everything easy, because nature seems to be more subtle than that. All right, so thanks for your attention.
Many thanks for the nice talk. Do we have any question?
So with quantum computers, we have speed up with respect to classical computers, right? Mm-hmm. But the class of computable functions is the same.
Yes.
Do you think we will be able to think about a model that will increase the class of computable function?
Mm-hmm. Okay, well, that's a very interesting question. Could anything change even the theory of computability? So let me just make it clear. A quantum computer does not do that. And the reason is that anything that a quantum computer can do, say in t steps, can always be simulated by a classical computer using something like 2 to the t steps, right? So, quantum computer merely gets an exponential speed up, which of course could, completely change things, right? Make things tractable that couldn't be done today within the lifetime of the universe, but it won't do anything like the halting problem, which is literally uncomputable. Now, people have thought a lot about this question. Well, could you build a physical device that could solve the halting problem in finite time, right? Which is to determine whether a given computer program will ever stop running, right? Or to do something which is literally uncomputable, in the sense of Turing. So to get that. We know something about what sorts of changes to known physics, would be seem to be necessary for that. This is not working. Let me. Here we go. So this Xeno computer, right? This machine that could do, first step in 1 second, second step in half a second, the third step in a quarter second, and so on. So after 2 seconds, it's done infinity steps. If you could actually build something like that, then that would change computability, right? That would solve the halting problem in finite time. Or, if you could stay far, go really close to a black hole event horizon, but not into it, and then far away, right? And then come back to your computer, right? You could accelerate computation arbitrarily, okay? So, why doesn't anyone try these things? Okay, well, we actually know something in physics. So here I'm going to try to tell you something about physics, right? About the difficulty of doing these things, which is that, if you wanted to speed up computation more and more, well, there are people who try something like that, right? They try to overclock their microprocessor, right? But if you run your microprocessor too fast, it will melt. That's why computers have fans in them, okay? But as you wanted to run your computer faster and faster, you would need more and more cooling, which would cost more and more energy, right? Now, you could just spend the more and more energy, but the problem is if you wanted to run your computer so fast that it did like 1 step per Planck time, 10 to the 43 steps per second. So, imagine just a photon bouncing back and forth between 2 mirrors, which are 10 to the minus 33 centimeters, or 1 Planck length apart. Okay, then that would require so much energy concentrated into so small of a region that your computer would then exceed its own Schwarzschild radius, which is just a fancy way of saying that your computer collapses to a black hole. Okay, I've always liked that as nature's way of telling you not to try something, right? But it's amazing to me that if not for gravity, if not for the Schwarzschild limit and things like that, it seems like maybe you could build computers that would change computability and let you solve the halting problem in finite time. Ultimately, quantum gravity is the thing that seems to rule it out. Yeah.
Any more questions?
So can you come back to the slide with the P and P?
Yes, of course.
So my question is that did you formally prove that no NP complete problem can be solved by a quantum computer, or is it just that you have not been able to find a smart solution?
It is the latter. So let me clarify that in terms of what can be rigorously proven right now, all of the classes in this picture and many more could all come collapsing down to a single class, right? We can't even prove that P is different from P space, which is everything you could do with polynomial memory, but up to an exponential amount of time. Okay, but I like to say that if we had been physicists, we would have simply declared these inequalities to be laws of nature. And maybe given ourselves Nobel Prizes for their enunciation. If they turned out later to be wrong, we just give ourselves more Nobel Prizes for their overthrow. Okay, but what we can say. So I tried to say this in the talk, but let me say it more explicitly. We can show that there is no Grover-like quantum algorithm that solves the NP-complete problems in polynomial time. In other words, there is no quantum algorithm that treats the NP-complete problem as just an abstract black box, right? As just 2 to the n possible solutions, where for each solution, the only thing you know how to do is to call some black box or subroutine that checks whether it is valid or not. If that's all you're doing, and most of the algorithm ideas that people have had, that's all that they are doing, right? Then you're only going to get the square root speed up of Grover's algorithm and no more than that. Could you exploit structure to do better? Well, yes, maybe you can. As far as anyone knows today, maybe you could even do that classically. That is the P versus NP problem.
Last question.
My question is about the P versus NP problem.
Yes.
So I know that there were many attempts to solve this problem and to prove that NP is separated from P. Circuit complexity, proof complexity, and geometric complexity. There's a reason that there's so much difficulty in doing this task.
Yeah, well, I think that it's an absolutely enormous problem, right? There is a lot of we know from the history of math that a problem may be asked, like even centuries before the tools are developed to even think about answering it, right? Like Fermat's last theorem, for example, or the irrationality of pi, for that matter. Okay, so P versus NP is asking for a universal statement, right? It's asking prove that there is no possible efficient algorithm to solve these search problems. That will ever be discovered, using any area of mathematics. Okay, and part of the difficulty is that there are really clever algorithms, right? There are other problems. I mean, no problem known to be NP complete, but there are many problems that look at first glance like they could be NP complete, but then they have some incredibly clever algorithm using linear programming, using semi-definite programming, maybe even using algebraic geometry, right? And so you have have to show that no tools like this, will suffice for the NP-complete problems. Now, I believe that. I believe it because there are thousands of problems known to be in P. There are thousands of problems known to be NP-complete. And for P equal to get P equals NP, all that would have needed to happen was that, one problem here and one problem here would have to coincide. And yet we never ever see it happen. So there seems to be like some invisible electric fence separating the classes. But to actually prove that, we've learned a lot actually over the last few decades about the extraordinary difficulty of proving exponential lower bounds in general models of computation. We can sometimes prove exponential lower bounds against models of computation that are much, much more limited than a universal computer. Okay, and even that is super hard, right? And so that gives, looking at those results gives you some sense for just how hard the full P versus NP problem is going to be, right? But I think it's not like we've made no progress on it. It's just that proving this kind of statement is a long ways off. Yeah.
Okay. So I thank you again, Scott Aaronson. I thank Philip Kim for the beautiful talks. And now there is a small coffee break upstairs in the second floor. Thank you to everybody.
Great job. Great job.